Afternoon? Afternoon. Have you taken your lunch?
Haven't yet.
Okay, good. Been informed that quite many of you cannot take attendance. Right. So maybe you probably have to try again after 30 minutes. Afterwards. In between. In between. If still cannot, then only I will take the attendance end of the class. Right. So tomorrow is holiday. Happy?
Yes.
Yes, good. Happy. It's the first time I hear students say holiday is good. Most of the time I hear students say, oh, not good, not good. They're going to rush the assignment, replacement class, all this. Okay, so I think I'm not going to wait for the rest, so we shall start our class. Shall we begin? Are you ready? Okay, yeah, good. So, as usual, before we start the lesson 3, some keywords from the past lecture 2. Some keywords. Give me some keywords. Yvonne. Test. Your friends. Help your friend faster. Some keywords. It's chapter 2. You got no friend. What is that? Goal formulations. So why do we need goal formulations? So chapter 2, as I mentioned, chapter 2, 3, and 4 are about parts, right? Parses algorithms. So what are the parses algorithms? For example, the map, right? The ways that you're using right now, like ways. You have a magic cube. Okay, an Excel parser. We have this cannibals and missionaries that we've seen last week. Right, all these applications. So where we need some algorithm to assist us to reach the destination, to find the goals in optimal solutions, right? So someone say goal formulations. What else? Jai,
Yeah, Jai.
Is it Jai? It's not mistaken. Let's try to remember my student names. Problem formulations. So we have a problem formulation. Okay, good. So what else? Under goal formulations, how many elements do we need to define first? 7. Goal formulation 7 elements. Goal formulation, how many elements? 3. Someone said 3. Very good. How about problem formulation? Someone said 7. So under the goal formulations, anyone remember the elements? We need to define for what? Goal, right? Where is the destination? So where is the goal? Second one, goal formulations, goal, destinations. Path. Path is under problem formulation. How to display the path. Very good. What else? Solutions. Oh, very good. Optimal solutions. Yeah. Optimal solutions. Right. The shortest distance, shortest station, least stations, least times. Right. What else? What's that? Abstraction. Very good. Okay, abstraction. Abstraction. Or the scope. Right. We need to define the scope first. Before we can, because now every time we can obtain so many solutions, right? Some of you, I know that you would like to achieve the destination or reach the goal in the least number of stations. At the same time, shorter distance. At the same time, least number of so-called time. So we cannot achieve so many optimal solutions at one time, right? So you have to set the scope first, make it more feasible. What else? We have 6 more elements here. Go test, very good. Right, go test. Normally we use if else statement to test whether the node, the current node, is it equal to the goal state. Yeah, yeah.
在这里厕所，那走过去。
Yeah.
没有。
What's your name? You want again?
自信。
No, you want this. This one?
温药。
Wen Yao. Give me one element here. Is there another 5?
Step cost.
Hmm? Step cost.
Step cost.
Okay, very good. So step cost. So what is step cost? It's the cost from one state taken from one state to another state. Another one? Path cost. Very good. So path cost. Path cost is total cost along the path. So this is the path. So you have to add A plus B plus C. So another 3 more. Go test, step cost. There's one very important element. There's one very important element. State space, okay. State space. To display, to show all the states. It's a space to display all the states. One more. It's very important one. Initial state. Okay, where do you start your state? Last one. Most important one. Function. What functions? Linear function. Quadratic function. Successor functions. Yeah. Successor. So what is successor? Let's say you have a state here, you expand. So this is your successor. The next node, the child node, successor function. In other words, it's a function to expand to the successor, to generate a successor state. Okay, so this is pretty important. So whether your algorithms works or not, it depends on this successor function also, which is very important. So this is the summary for chapter 2, the planning. I would say plannings or the goal of problem formulation before we decide which algorithm to use. So once you define these 8 elements here, then the next step would be the algorithms. Okay, so all the algorithms. So these algorithms we can split into 2 categories. The first one is called uninformed search. Sometimes it's called blind search. Another one is called informed search. Sometimes called heuristic search. Same meaning, right? So sometimes they call it uninformed search. So in the chapter 3, we will focus in this topic, which is uninformed search. So whatever from diploma, then you're probably very good in this. Anyone? So then I can ask you more questions. Alright, so we have an uninformed search. So later on we are going to cover some of the very famous typical search in the uninformed search. For example, breadth-first search, depth-first search, and then these are the 2 main. So we have more variation from the main. For example, bidirectional search. We have an iterative depth first search, and so on and so on. The variations of the breadth-first search and depth-first search. So what is uninformed search? If you look at the terms here, it means unmeans, but no, right? There's no information. Okay? It means that you're going to do the search without any information. There's no information is given to you. And let's say now you have in a dark room, and you're inside a map, something like this. So let's say something like this. Okay, and then this. Okay, so this is the goal, let's say. So now you. So this is inside a dark room. There are no information is given. So how are you going to reach the solutions? So how? You just basically just try an arrow, right? Just bang. You can just walk. Okay, somewhere around there's a barrier, bang. So you just turn, bang, then come out again, try, and then you reach the goal, right? Okay, so the so-called blind search. No information is given. It solely depends on the patterns that you define. You follow a certain pattern to do the search. So what is the pattern? For example, you follow this sequence: up, left, down, right. So this is the pattern. So I will always follow the straight if there's no barrier. If there's a barrier, I move to the second pattern, which is turn left. Okay, if there's a barrier, I continue, turn down, for example. So you follow a certain patterns to do the search. Okay, so it's called uninformed search. There's no information given to you. The information here means maybe the time, the distance, maybe some other information will assist you on which part should I depart now, based on the information. But now there's no information. It solely depends on the pattern. Then you just try and error. Okay, so. Yeah. Okay, meanwhile for informed search means that the information is given. Okay, the information is given, for example, the distance between the state to another state. So the information is given so that you know that, oh, this distance is shorter, so I should go to this direction. So I reach the current state, then I check. So which distance is shorter? Oh, this distance, so I follow this path. So it's called informed search. The information is given so that you can make a better decision where is the next move. Uninformed search, that no information is given, you just try and error, follow certain patterns. Okay, so this is just a recap. So I'm going to skip it. Okay, so we are going to cover the two main strategies here, uninformed and the informed search. So for uninformed search, as I mentioned, we will cover focus more on towards the breadth search and depth search. You'll see in the market or in the Google, maybe probably there are a lot of uninformed search available. For example, depth limit search, iterative depth deepening search, bidirectional search, and a lot more. Okay, but those are actually expanded from these two main search here. The idea is actually originate from these two. They just change some strategies or to make it better. Okay, so but however, I don't think there's any application using uninformed search. This is not a good search, which take a lot of time. Mainly we use informed search in most of the applications. But however, in order to give you explorations about what is search, so this is good also to let you know how the fundamental of the search, how it works. So let's start with the breadth first search. So this is breadth first search. Breadth first search. Not very fancy. Okay, what is breadth? What is breadth? Can you search? Can you search Wikipedia or Google? What is the meaning of this BREADDH? What is the meaning of this word breadth? White. White. Very good. What else? White. What other meanings given by the Mr. Google? It's like white. Okay, very good. Distance from side to side. Okay, so you have a distance from side to side. Okay, so in overall, the meaning of breadth means horizontal. Right? You'll see that it's white is about the horizontal directions. Distance from one direction to one direction is about horizontal. It's about white, right? So it means that how the breadth search work. Breadth search work. Okay, look at the definition. All the nodes are expanded at the given depth in the search tree before any nodes at the next level are expanded. It means that, let's say you have a state space, something like this. Okay, so breadth search will work horizontally. They will do the search in horizontal way. Started from here. Search whether is it equal to goal state? No. Search horizontally. search, search, search. Until there's no solution, what? Go to the next level. Go to the next level. Start from the left hand side, search again. Search, search, search. Until there's no solution, go to the next level. So it's look like a Christmas tree horizontally. So it's all breakfast search. Okay? Horizontally. Okay, so this is the algorithm for the breakfasts. It's always begin with the root node. So this is the root node. Examine all the nodes in each level. So it means that you will check all the nodes in each level. So let's say this is a level 0, level 1, and level 2. So you will check level by level. Level 1, check all the nodes, whether is it equal to go. So in this case, you have to come back to this go test. Okay? So we need to check whether is it a go state, is it equal to go state? No. Expand, check. Search, 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 search. Okay, until it reaches the goal. Repeat the process and work downwards, right? Work downwards from left to right until the solution is found. Means that there's no solutions, go to the next level, search again. No solution, go to the next level until it searches the solutions. So therefore, breakfasts guarantee a completeness. Definitely will give you the solution because it searches level by level. Return fail if there's no solutions. If there's no solutions, then it will return fail lah. But most of the time no lah. So definitely we give you a solution. So for example, in this map here, so this is very simple. We have a simple map. They give you the state space already. How to do the search? Horizontally, like AD, search, 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 search until it reaches the goal. So how about this? Can you tell me the sequence of the state? Okay, how the search works? If the initial state is R and the goal state is O. How the breakfast search works? From R first, then A, then M. No solution. Go to next level. B, J, N, P. No solution. C, K, O. Solution. Stop here. Okay. So this is very simple because the state space already arranged in order, right? Arranged in the level by level. So later on, I'm going to show you some example where we have a very messed up map here. So how are we going to use the preferences to do the search? So, okay, but they give you the idea first. So how preferences work. So after we perform the preferences, how do we know whether it's a good algorithms? So it depends on these 4 criteria. Completeness for preferences, yes, definitely. Completeness, right? Because you check level by level, you will definitely return you solutions. Optimality, yes. Optimality, yes. Confirm. It will definitely return the optimal solution using preferences. It means that the least number of stations. Okay? Because there's no distant information. The only information we have is the station. So the optimal solution is least number of stations. By using a preferences, it guarantees optimal solution because it checks level by level. Okay? Meanwhile, the time and space is depends. The time and the space, it depends. If your solutions placed far away from the original nodes, then it's going to take a lot of time. Okay, so it depends on the time and the space, it depends. But most of the time, the space is a lot. Okay, why space is a lot? Because you need, space here means that the memory, that you need to store the nodes. Whenever you expand here, you expand 3 nodes here. So these 3 nodes, we need to store inside a memory. In order to store the memory, if you didn't store the memory in the memory, how are we going to expand, right? How are we going to expand in the first node? So we need to store inside the memory first. For example, this is BCD, right? So the moment we search, we need this information in order to generate these 2 nodes and search again. So then we need to store these 2 nodes again, maybe for example here. So it means that if your space is very big, then you probably need a huge memory to store all the information for the nodes. Okay, the space for the preferences normally high. Space, the time, it depends. It depends the location. Where is your goal? Okay, so later on I'm going to show you one example, a comparison between the preferences and preferences in terms of the completeness, optimality, and time and the space. Okay, don't worry. So this one we will skip first. Okay, now let's move on to the depth first search. So I'm going to use that whiteboard. So what is depth first search? So before we go through the algorithm for the depth first search, what is the meaning for depth? Can you search? What is the meaning of depth?
Deep.
Deep. Okay. Somehow right. Deep. What else? Vertical. Very good. Okay. The kind of vertical directions. Right. So in contrast to that, breadth first search is about horizontals, right? Wide the distance. So depth first search is horizontal. Horizontal. Okay. The direction is slightly different. So let's see how the algorithms for depth first search work. Always expand the deepest node in the current fringe of the search tree. Nodes leading from that end will be discarded from the memory. Then the search will back up to the next lowest node to as an explore successor. So it means that, so now we have a node. We expand first. Right. We search, we do the search. So is it equal to the goal? No. Check. Is it equal to goal? No. We continue to search. You look at the breadth first search is horizontal way, right? Depth first search is we search horizontally. Search. Search. Let's say the E is a dead end, no solutions. What happened? We do backtracking. What? We constant balik. One node before, and see whether we have a node that can be expanded from the D. If yes, we continue from here. At the same time, we will remove E from the memory. Okay? If you look at the breadth first search, you have to store every single node in the memory. So it takes a lot of space. But for the depth first search, as long as you meet the dead end, this one can be removed from the memory, because that we know this node is not going to give you any solution. So we can just remove from the memory. Then your memory size will be so-called smaller compared to the breadth first search. Okay, we can continue E, F, G for example. G is a dead end, for example. So we can remove here, backtrack. Maybe F cannot generate, we can backtrack. So maybe D no more, we can backtrack. So maybe C we have another solution, H. So the whole chunk here we can remove from the memory. Then we continue to expand. So you just at this moment you just need to store 4 nodes in the memory. But for that purposes, you need to store all the nodes in the memory, whether you like it or not, because we need the parent node information. We need the parent node information so that we can expand from the parent node. Is that clear? For the depth first search and breadth first search. Okay. So you will see sometimes you will see they have this kind of words called LIFO, last in first out. Meanwhile the breadth first search is called first in first out. LIFO. I'm going to show you what is the before and before later. Okay, for example, this one, A. So A, we will focus on one part first. We don't expand C, we expand B first. Okay, C, we put it inside some memory. We don't disturb the C. We expand B. Continue. Expand. Check whether D is it a solution. D is not a solution. Expand again. H, is it a solution? H is not a solution. So we backtrack. Check. I, is it a solution? No. Backtrack. Backtrack. So this one all can be removed from memory. Expand to E. E to J, no solution. Backtrack, expand K. This whole chunk here is not a solution. Not going to give you any solution. Remove from the memory. Expand through the C. Continue. F. L is not a solution. H. So eventually, how many nodes that we store? Only 4 nodes here. Okay, so this is how the depth first search work in vertical way, in the vertical directions. Breadth first search in horizontal directions. Is that clear in this case? Okay, good. Good, huh? So same. So after you use the depth first search, any strategies that we use, no matter is a informed search or uninformed search, these are the 4 criteria: completeness, optimality, time, and the space. So what is this OVE here? Is actually another story. I'm not going to cover this. Okay, so but however I use the example to show you how to compare the time and the space later. Alright, so I'm going to show you how to generate the state space or how to do the search using breadth-first and depth-first search. So let's say now we have these questions, which is the octal puzzle. We have a 1, 2, 3, 4, 5, 8, 7, and 6. So in this case, no state space is given. If no state space is given, then we have to use the depth-first search and breadth-first search to do the search for us, right? So in the next example, it's slightly different. The next example, we have the state space, okay? But this one later. So let's see the questions without the state space first. Alright, so in order to solve this, the questions, first step, you have to define the successor functions. What is the successor function? You still remember last week we covered one of the questions here, and we defined the successor functions. Okay, so reach the next state to the current state. What is a successor function that you can define from this case? Can you give me some example? What is the successor functions for this case? Successor function is what? Functions that so-called it defines the move, right? Change from the current state to the next state. What are the possible movements? Okay, very good. So one of the way that you define successor function is you can move the empty tiles, right? You move the empty tiles. Follow these maybe directions. You have to state the sequence, maybe up, right, down, left. You yourself, you have to set the directions, okay? So that is the first state, the next state. So let's say this is the breadth-first search. So this is the depth-first search. So the next, the first state is 1, 2, 3, 4, 5, 4, 8, 5, 7, 6. Always follow this sequence. Okay, so breadth-first is what? You expand all the nodes, right? Expand all the nodes, right? And travel horizontally. Okay, so follow the first sequence. Move up, yes. So so where this is moving up. Then you can move right. Move right, yes. 5, 7, 6. Okay, so this is move right. And then follow the sequence. You cannot jump from here to here. You have to follow the sequence. This, and this. Move down, cannot. Move left, can. 7, 6. So this is move left. Okay? So no more solution, right? You expand from here, here. Continue, next level. Because there's no solution in this level. So this is level 1. No solutions. Your solutions is 1, 2, 3, 4, 5, 6, 7, 8. Okay? Continue the expand. Reset this sequence. Can we move up? Yes. 1, 3, 2, 5, 5, 7, 8, 6. So this is move up. So can we move right? Move right? Yes, can. 1, 2, 3, 4, 5, 7, 8, 6. So this is move right. So we have move down. Move down can, but it back to original state. So remember, in any search algorithms, we avoid repeated states, right? So you can move down, right? You can move down, but it back to original state. So move down, we don't take into account. Move left, yes, yeah, you can move left. So you move left. Alright, so no more solution, right? No more solution. Continue with this one, expand. Okay, so this one move left. Can we move up? Can, yeah. And move repeated state. If we move up, this one 1, 2, 3, 4, 8, 7, 6, 5. Can we move right? Cannot. Can we move down? Cannot. Can we move left? Can. But it back to original state. So no more. So there's only one successor from the current state. Continue from here. Can we move up? Yes. So this is 1, 2, 3, 4, 8, 5, 7, 6. we move right? Yeah, you can move right, but it back to original state. So we don't move right. Can we move down? Cannot. Can we move left? Cannot. So that is the successor for level 2, right? So then we continue. Okay, so we continue. So I think the answer is somewhere around here. Somewhere around here. It's okay. We expand from here first. So this one, continue. Can we move up? Cannot. Move right? Yes, can. 1, 3, 4, 2, 5, 7, 8, 6. Up cannot, right cannot, down can. So this is move down. 1, 2, 3, 4, 5, 7, 8, 6. Move left. Sorry, if go down, then it's back to original state. So we don't want. We want to move left. So move left. This one. Okay. So normal solution continue from here. Okay. So move up. Right cannot, down. So this is the solution. That's the solution. Okay. So how the algorithm works? The algorithm will return you this. So this is the search path. So it will search from here, search from here. But as a user, what we will see is from here. Okay, this. If you play the game, you ask the that preferences return me the optimal solution. It will give you only 4 steps. Okay, you can slide this empty tiles up. After that, you slide to the right. After that, you slide down. Then you reach the solutions. So it means that the return path will be what will be this. I'll give a state called A. This is called maybe B. I'll call it as C lah. This is D. So the return path is A, B, C, D. But the search path will be this. Okay, so return path and the search path is 2 different paths. Okay, return path is where the user which path that you can reach to the optimal solution from here straight away. You have only 4 stations. How the algorithms do the search? You need to search from here. Search. How many stations to search? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 13 states to traverse to do the search. Okay? So meanwhile, how the depth first search works? So depth first search is slightly it depends on solution also lah. Let's see whether we can reach the solutions. So how depth first search works is focused on only one direction. Go up, right? 1, 2, 3, 4, 5, 7, 8, 6. Go up, right? So we want to expand another level. Whenever we want to expand another level, reset this one. Move up again. 1, 2, 3, 4, 5, 7, 8, 6. Okay. Go to another level. Move up again. Cannot move up. We go to second sequence. Go right. 1, 3, 4, 2, 5, 7, 6. Continue until you reach the solution. Or there's no solution, you do a backtracking. So unfortunately, until level 4, we haven't get the solution lah. So we have to continue. We have to do it. So this one, optimal completeness, optimality, yes. But since we didn't get the answers for this, so I cannot compare the time and the space. The next example, yes, we will compare. But in this case, we cannot compare much. So this one completeness. If you continue to expand, you will definitely get a solution also. But you have to continue to expand. Okay, but not optimal. So how do we know that it is not optimal solutions? You have to always take the preferences as the reference. Because it is understood that preferences will definitely give you optimal solutions. So we know that for preferences 1, 2, 3, 4, only 4 stations. Only 4 stations. But in this case, 1, 2, 3, 4, you haven't get the solution yet. So you will definitely need more than 4 stations. It means that this one is not optimal solution. We will not give you optimal solution. How to know? Always use the breakfasts as the reference. Okay? Is that clear? Okay, good. Okay, shall we continue? Yes, still okay, Okay, look at this. Anyone? None of you from diploma, I don't believe. Anyone? No, really no. 0. Okay. Brandon. Where's Brandon? Oh, sleepy. Okay, anyone help me to wipe? Oh, thank you very much. And here, this everything. So I will give you first. Okay. Okay, thank you. What is your name? Ong Shi, thank you. Okay, so this one is okay. This one okay. Maybe this part. Maybe this part. This one. Start from here. This is the summary. Until this one. Okay, thank you. Oishi. Oishi. Oishi, Can I call you Oishi? Up to me. I have to change name. Otherwise, this is the way how I remember my students. Okay, so let's see this question. So this is a state space. Okay, so this is a space. It's kind of a map, So you have maybe from A you can traverse to B, B you can traverse to E, you can travel to F. So it's kind of a map. So you can assume that A is a tie UMT, B is a TT and so forth. Right? In this question, you would like to travel from A and reach station J. Ignore the value inside this map because this is uninformed search. We are using uninformed search. Ignore the value inside this map first. Okay? So what is the optimal solution? We would like to reach the destination in the least number of stations using breadth search and depth first search. Okay? So we have some unidirectional and bidirectional here. What is unidirectional? Means that A can go to B, B can go to F, but F cannot go back to B. You have to follow the direction here. So you have a bidirectional here. You have a L can go to H, H can go to L. So now, let's find the optimal solution, or not the optimal solution. Find a path from A to J using breadth first search and depth first search. So let's try with the breadth first search first. Okay. Remember, breadth first search is horizontally. Before we start, I will always restore this column, or I call it as in practical, it's actually an array. To store the node is going to expand, and the node is already expanded. I will call this as open and close. Okay, so open is the node, is the place to store the node it is going to expand. Okay, so closed list is a node, is a place to store the node that already expanded. It's already expanded. So easy for me to track whether there's a repeated state or not. Okay? So start from the beginning. Okay? A. So this is the root node. So this is going to expand. So I put A first. So the moment I expand, I will put an A inside a closed list. So A expand, you will get B, C, and D. Assume that we have to expand follow alphabetical orders, A, B, C, D, E, F, G. Yeah? So we will get B, C, D. So we will get B, C, and D. So these three nodes are the nodes that is going to expand. It's not yet expand yet. So we will store these three nodes inside here. B, C, and D. Okay? So always start from the left hand side. Expand B. You will expand B, you will get E and F, right? So you will get E and F. So where to put? So for breakfast search, you add behind. Okay, add behind. So B, you will get E and F. So you have E and F here. So you will have E and F here. Okay? So next, expand C. Follow this open list, alright? Expand C. C, this is the place that already expanded. So we want to expand C here. So C will give you D, G, and H. D, G, and H. Follow alphabetical orders. But D is already expanded, so we put a dotted line. It indicates that C can go to D. D, G, and H. So we expand G and H. Okay, so add the G and H behind. Okay, now expand D. So expand D continue, you will get what? H and I. H is already here, so we just put a dotted line and I. So we have E, F, G, H, I. Okay. Continue expand E. E, it can go to, look at the graph, E can go to F, so it can go to F. Beside that, no more. Means that it already made the dead end. E cannot expand anymore except F. So it's okay, we continue F. Expand F, you will get K, right? You will get K. So K append here. Okay. So after that, expand G. Expand G, you will get F and J. Okay, G, you will get F and J. Okay, so J, put under here first. It's not yet reached the goal because we will only stop the search only where the node inside the closed list is equal to goals. So whenever you expand here, you have to check whether is it equal to goal. No, expand, check. Okay, check is it equal to goal. It's not equal to goal, continue to do the search. Okay, H. H you will get G and L. So G and L. So add the L behind. Okay, expand I. I, you go to L. So I go to L. No more, right? No more. Okay, so you have no expanded node from the I, it's okay. Expand K. If expand K, whereas you go back to G, right? So you can go to G. Beside that, it's also that end, right? No more solutions. Expand J. J, is it equal to go? Yes. So we stop it here. So this is how the algorithm do the search. You search from the A, search B, is it search C, D, search. Okay, stop. So that will be the solution. So how the search path, what is the search path? A, B, C, D, E, F, G, H, I, K, and J. So this is the search path. Okay, so this is how the algorithm search. So what is the return path? So return path is the path that will lead you to the solutions. As a user, what is the return path? Return path will be A, C, G, and J. follow me? Cannot. Under this stage. Cannot. Start from there. Beginning. Okay, it's okay. I'll continue first. So this is actually the search graph. Okay, sometimes you will see that draw the resultant tree. So what is the resultant tree? Resultant tree is you will search from here, search until J is the goal. So this is your resultant tree. This is your resultant tree. Okay, so we will continue with the depth first search first. I want you to see the comparison between depth first search and breadth first search. Okay. Alright, so use the same graph, so use the same state space, draw the depth first search. Use the depth first search. Okay, depth first search. Always start from the open and the close. During the exam, you don't need to draw just open and close. The purpose I use the open and close is for me to trace whether I have a repeated notes or not, whether which note is start to expand. If you know very well how to expand, you can just draw that graph. It's okay. If you are not familiar with this, then you use this to assist you to draw the graph. Okay? So start from the A. Sometimes the open here in the depth first search is so-called stack. You will see in some of the Google, some of the websites, they use stack. Sometimes the open here, they use what? Frontier. It's just a different name. Different names. We use open and close. So A expand what? Expand B, C, and D. But in the depth first search, remember, we focus one direction. Vertical. Right? Vertical. So A, expand A, we will get B, C, and D. But however, we focus on B first. C and D, we don't really expect because this is depth first search. But however, we will still put the B, C, D inside the open so that if let's say B is the dead end, we know which node to expand next. Okay? So we have a B. B expand, you have what? E, F. So we have E, F. So in the depth first search, you add in front. It means that the node that you're going to expand, you add in front of the open list. Just now, we add behind. Right? For example, B expand E and F. So we store the E and F, add behind the list. So in this case, we add in front. What does it mean? So we have an E and F, so we add in front. So we put the E and F in front of the open list. Okay? So next, expand E, you will get expand E, you will get F. So we will get F. So we will put an F here. Okay. Expand the F. So we get K. So K add in front. Okay. K expand, you will get G. Okay. So expand G, you will get J. Expand J, is it equal to go? Is it equal to go? J, is J our go? Yes, so we stop it here. Now, so you will see the two totally different graph here. So what is the search path? The search path follow the closed list. You will start from A, search the B, E, F, K, G, and J. Done. So what is the return path? Return path A, B, E, F, K, G, and J. A, B, E, F, K, G, and J. So accidentally, so coincidentally, you see the search path and return path same lah. But in some occasions, they are different. But in this case, they are the same. So you see that which one is optimal? The breadth first search only 4 stations to give you the goal, to reach you the solution. But for the depth first search 1, 2, 3, 4, 5, 6, 7, it takes 7 stations to give you the solutions. Okay, so we can see that Both also give you solutions, complete. This one complete. This one optimal solution. This is not optimal. This is not optimal because it takes more stations to give you to reach the solutions. Okay. We talk about the space. Space consumption. Okay. You see how many nodes that we need to stop? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 nodes to stop. So this one, 1, 2, 3, 4, 5, 6, 7. So this one, low space is required. This is more space. Okay? So the time, you can assume that the moment I expand one node, it takes 1 second, for example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It takes 10 seconds to expand. So this one, 1, 2, 3, 4, 5, 6 seconds, for example. So this one also time consuming. This one less time. So these both depends on the situation. But in these examples, the devices take lesser time and the lesser space. But however, it is not optimal. In this case, yes, it is optimal. But however, it consumes more memory and also time. So it depends on the application. If you prefer optimal solution, then you have to choose for preferences. Okay? If you don't care about the optimal solutions, if you care about the time and the space, then you choose preferences. Okay? So can you try this exercise later? If you cannot, then you come back to me again. Okay. Sleepy already. Sleepy. I'm so sad. Okay, so we do have another example or exercise in the tutorial 3. Okay, so I hope that you can take that chance to polish your skill for the depth versus or breadth versus. I would say definitely there will be one question from the depth versus or breadth versus or uninformed search, either in your midterm or in your final. Okay, so you have to practice yourself how to generate the so-called resultant tree. So this is the resultant tree, and how to generate the so-called the return path as well as the search path from the graph. Okay, so you can go back and try to take out a piece of paper, try compare my answer. If you still cannot get the answer, then I will take another slot next week to explain again. But I want you to try first. Okay? Alright, so I think we should take a rest for 10 minutes. We will come back in 1:10. Okay?
然后发现他做 KOL 因为传世，做 KOL 传世，教我每次打靶是
DBS 像 DBS
然后我们做 KOL 传世啊，那边是有另外一个火车站，这个，所以我不用见到巴士站拿出来。那你去到那边那个大概
是要过对面是吗？
就你上了那个楼梯啊，你到这边还要站到嘛，上楼梯转左是去巴士站，你转右的话就是去那个 LD， 那个 LD 坐到阿尔上，你坐那个LD。 坐到阿文的上去，然后到那边看你搭巴士还是走路就能到那个保育点。
它这个签名是什么东西？是多巴士？这样很远。等下你回去，那你回去的话就把那个面包放在冰箱。
哪个？
啊？
哪个？
那个纸箱那个麦克风，放冰炒跟冰。因为它是煎到期的，怕等下放在外面的话，两个很容易长，就是长得更确定。所以我就想先放冰室。
大约4个小时。这老师没有到4个小时。
所以你是给他煎到晚上6点。
手压
Okay, welcome back. Are you still with me? Yes, sir. Yes, I'm still with me. Yeah. Alright. So, if you look at the third example, so this is actually a block problem. So I'm not sure whether you play this game or not, where you have to actually place the block. You have an A, B, C, D, E, 5 block here. So you have to place the B, E, stack the blocks one to another, and until you reach A, B, C, D, E. In this case, I don't really encourage you to perform the price search using you mean solve this problem using a price search. So it's going to give you a very long state space, and it's not effective at all. And how are you going to define the successor function also and other problems? So this one I will keep it for the heuristic search, which is the informed search. I will show you how to use the informed search to reach the solutions. I'm not going to use the price search. It's not effective. So I will skip this question 3 for next week. We have so after we have a depth first search and breadth first search. So there's another search. It's called depth first search. Okay, so in the depth first search, there might be one problem or the limitations called infinity loops. So in some state space, you might have some solutions or the state space look like this. It's in a cycle, or sometimes it is infinite. So something like this. So you have a very big state space. This is like we call it as a infinite graph. By using the depth first and breadth first, yes, we can read you to the solution if, let's say, the state space is finite. Okay, but sometimes you might have infinite path. If let's say if you have an infinite path, by using depth first search, you may not able to reach the solution. It means that you have to keep search, right? You search, keep track inside here, or maybe infinite. You search until there's no solutions. It might happen. So in order to avoid this kind of so-called trap inside the loops, so someone introduced the depth limit search to avoid that trap inside the loop. So how the depth limit search is where we have to set the depth first. This is one of the parameters. So let's say D is equal to 5. So we will do the search only. This is level 0, level 1, level 2, level 3, level 4, and level 5. If there's no solutions, we stop there. We don't continue the search. We don't continue the search, we do backtracking. We search. Whether if there's solution, no more. We backtrack. Search. We set the limit D to a certain number to avoid trap inside infinity loops. But the problem for the depth limit search is, how do we define the D? We don't have any standard way or any so-called any guideline to set what is the proper value for the D. So this one we have to try and errors. So in order to solve this depth limit search, someone developed another solutions. Another search is called iterative deepening depth first search. So what is iterative deepening depth first search? So come back to the depth limit search. So iterative deepening depth first search is where we set a D as well. For example, D is equal to 5. So we search. If there's no solution, for example like this, no solutions, search, no solutions, then we will open up this limit. We will add the iteration, maybe increment by 1 or maybe by 2. Then we continue the search again. If let's say now we add to D equal to 7, we add the variator search. If there's no more solution, add more, maybe 1 or 2. You iterate it. You add the D value. We increase the value of D. So not very important lah. And then the last search is called bidirectional search. So what is bidirectional search? Is where we do the search in two directions. In two directions. Let's say now we have a initial state. We know that this is our initial state. We know that this is our goal state. So we will expand from here. Let's say you have a tree nodes. So goals that you can backtrack is actually reach from maybe another tree. We do concurrently. Then we continue the second level. Maybe this is another level. 2. This is 1. Maybe this is that end. Maybe this is that end also. Maybe this is come from the 1. So this is another 1. This is another 2. And then we continue. Maybe this meet to this path, right? So this to go to other way around already. Okay, this go to others, this go from others. So then we know that this will be our solutions. We start from both directions. Okay, we start to expand and then backtrack, and then you somehow have a center point or you have an intersection point. Then we will stop the search. Okay, is that clear? So, but however, these three searches are not really famous lah for the interactive depth limit search and also bidirectional search. Okay, as long as you can understand the depth first search and breadth first search, that is good enough. Okay. Okay. So, any questions so far? If no question, then I have a question for you. So, can you try this question? It's one of the past question back to 2022 October. So can you try this? So you have a 2, 4, 6, 7. You have a 7 nodes here. Okay, design automated driving car. You would like to start from A. Your destination is G. So assume that all distance are equal, but in this case, we don't care about the distance because this is blind search. So look at question A. Suppose agent Z is required to drive from A to G. Using breadth first search and depth first search, draw resulting search tree with the node expansion in alphabetical order. Okay, and at the same time find the return path. Okay, so I give you 10 minutes. Try this question, then I will know your understanding, whether you understand this depth first search or breadth first search. 10 minutes, 10 minutes. At the same time, try to sign again. See whether you are able to sign again. 901966.
这个是不是像组合一样？
reference 是组合的。
对，这两个 A 去 G， 所以是 A 一开始，然后分支 B、C 是不是？
应该是这样看的。
我这样看。
我觉得。
Same one. It's saying congratulations. If not same, then you have to try again. Okay, so look at the question lah. So from A generate references B and C, right? Generate B and C. So this is another level. So always start from the left hand side, generate from B. B can go to donkey and F. Donkey and F. Okay, no more. So, okay, so horizontal D and F. So C give you what? C give you E and F. So F already here, right? So we just put a dotted line. Okay, if you don't put it's okay also. So we have an E and F here. No more solutions. Next, donkey. Expand from donkey, you will get G. Okay, so that is your resulting 3. Okay, so how the preferences do the search, right? Search like this. So what is the return path? A, B, D, G. So this is the return path. What is the search path? A, B, C, D, F, E, and G. How the algorithm do the search? From this way. So that process very simple. A expand to B, B can expand to D, D can expand to G. Now this is your solution. Stop it here. So that is your resulting 3. So what is the return path? A, B, D, G. What is the search path? A, B, D, G also. Okay. So if you compare both completeness, yes, both give you the solution. A to G, yes, both yes. Is it optimal? Preferences guarantee yes. So preferences take how many stations? 1, 2, 3, 4. 4 stations. Preferences 1, 2, 3, 4. Also 4 stations. So both also give you optimal solution. You look at the third one about time efficiency. Time efficiency, whether is it time consumption and time efficiency is two different things. Time consumption is high or low. Time efficiency is it take faster to reach the solution or lower, right? So in this case, that person definitely take lower because you go straight away 4 stations. This one you have to go from here. So the time efficiency for this case is very low. Okay. Meanwhile, for the space consumption for this case is definitely low more because you need more memory to store all the nodes. But for that person, there's only 4 nodes. There's only 4 nodes. But you just need to store 4 nodes compared to the preferences. Okay? Good. So, how about this? Another question. This is midterm test. You probably won't get it from the intranet. So this is a partial question. So the question 1. A Russian novice proposed 4 different types of AI. So this one I think you should know lah. This one is in the tutorial. So we have a act like a human, act rationally, think rationally, and think like a human lah. So question 2 is about blind search, differences and preferences also. I think this one is more complicated compared to this question. Yeah, you can try this, and then after that shows the return path as well as the resulting 3. Okay, but sometimes the question may ask show the search path. So this one is return path. Sometimes you are required to show the search path also. And compare the performance in terms of only completeness and the optimality. Okay, so I'll give you another maybe 10 minutes. 10 minutes.
return path 就是
你的答案
就是那个你
最短的那条路。
还睡吗？
怎样分辨哪一个是第一行，哪一个是第二行？
他要跟你讲不是，这一题他讲是叫你从根据 alphabetical order 所选的哪一种，就是从 A 开始。
A 到 H，你讲懂这是第一行，然后这是第二行，然后第三行是这样子。就是我说一直排的这个排的这个流程。
对，整排的在说人。
回去。
So I want you to try first, so next week only I will show you our answer. Okay? So you go back and try first. Boleh? Okay, yeah? Alright, so that's it for today's chapter 2, but chapter 3. So but before we end this class, I would like to show you some AI related projects that give you some ideas on like how you give some ideas on your maybe assignment or maybe for your F5P projects. Some of the projects here are actually from my F5P students. Some of them are actually from the assignment. Mainly I extract from image processing because there's something to show you. For electromagnetic system or chatbot, I don't think I have that video. I forgot it. I extract from during the MCO. The live presentation, so I will just extract some of the project from here. Okay, so the first one is using a deep learning or machine learning to predict the stock trade, the order price. So these are actually a F5P project done by these students. So you can actually scan this the QR code, so it will lead you
我
to
其
the
实也不太
platform.
确定哦，
You
因
can
为
just
如果
key
based on my
the
rules 的话是讲说，
so-called the stock
它会
name.
因为
And
reverse
then
charge 是全部一直要打那
behind,
种，
so we will use the
然后找到
LSTM as
它是
well
最
as
完整就
there's
可
one
以
more algorithm, I cannot remember
这
the
样每一
names.
个可能
So
是
they
有
will
一个
train the historical data of the data set, and then to predict the stock price. So you can scan and then you can put it out, but it will take a lot of time because it involves a very so-called deep learning. So you will see that it take a lot of time to produce you the result, and as well as the hardware problem. So okay, so this is the first example. So the next example will be the so-called eczema tracker. So what is eczema tracker? It's actually a mobile app. So they integrate this AI module into the very simple AI application here. So the purpose of this object is to identify the eczema level. So what is eczema? It's actually a skin disease. So there are several levels on this skin disease. So this company called Lipid Group, they approach us and so-called collaborate with us. So their requirement is to build the apps for the user use so that they can scan their skin conditions, and at the same time we will provide the user their eczema level, whether is it in the level 2, whether in the level 3. So beside that, so we need to provide them also during, for example, week 2, what food they actually consumes here, and also week 3, so that we can do a comparison, right? Let's say in this case January, so we see that from the week 2, the eczema level is in the level 4, it somehow dropped to the level 2 in the week 3. Then based on here, we can actually see the summary, right? What are the food that actually you consume, or maybe other environments where you can avoid or maybe reduce the eczema level. So you can also scan this QR code and get the apps. You can actually install the apps and sign up as a user. Then inside this app also there are some other features. For example, you can purchase the product from this company. So this company actually provide the solutions for the eczema. So it's actually done by quite many students. So we spent quite long, I think 2 years to complete this. So this is also another project where the students find out that some of the Chinese herb are actually look like similar. So they build a simple app, use a deep learning, again train the models to identify or to classify these 3 different the Chinese herb. So you can also scan the QR code. So it will lead you to the drive. You can install the apps and play around with it. But it can only classify 3 different herbs. So if you need to more detections, then you need probably put in more images. So we have more crack detection here. So I don't think this link is workable now. I think the link is not working anymore. So what is this? Is actually to build the application to detect the wall cracks. So why do we need to detect the wall cracks? It's because we found that quite many buildings, high-rise buildings, for example, the condo, if there's any damage there, we cannot detect. So we use the drone to actually capture the image surrounding the buildings. Okay, and then this image will send to this so-called neural networks and to identify the wall cracks. So then we will have a dashboard to identify which area, which region we have a crack, what is the crack width, all the informations. Then we will take action, maybe go and repair the buildings or the wall. This is I think this is an assignment. Yeah, this is one of the assignments. So students build the apps to identify different fruits using different algorithms. They have actually done a very good job. Only 2 months or 2-3 months they built this app. You can see that there are 3 different algorithms to identify the orange and then the so-called melons. The melons. Then show you the confidence level. So it show you what melon 100%. So this is another models. So another algorithm shows that this is a melon, only 81% of confidence levels. Orange is 30%. So this one shows cucumber. So this is not true. But they did mention what is the reason why the confidence level for this is very low, because they are using image on the internet, not the real image. So probably that would be the root cause of the reason why. So we have face recognitions, project, real time, or also using the images. Besides detect the face, it also identify who is this person and as well as the genders. So this is a real-time face recognition. It's quite smooth, so you will see that the name is down here as well as the genders. This is sentiment analysis. It's not related to image anymore, but they would like to study the sentiment of the comment after someone bought the products or the items from the Amazon. So they leave a comment. So we would like to know the comment whether is it a positive or negative, whether this product is good or not. So we can actually crawl the data from the Amazon, the reviews, and then perform some machine learning, identify whether this is a positive review or a negative review. So and then this project is actually divided into three different modules. Crawl the data, perform some pre-processing, and then the last one is to perform the machine learning. So it's actually performed by these three different students. So the first one you can see that just now we have how to crawl the data, and then the second one would be the image the pre-processing stage here. So we have a raw data from the internet. We had to perform the data pre-processing on the text. And then lastly, we have a last student to perform the machine learning. Okay, so we use a different algorithm, for example, the 9 bias, and what else? I support vector machine. Need to perform the calculate, and then eventually you will see that the comment, right? This is actually the comment. So what is the whether it's a positive comment or negative comment? So it will show here it's a positive comment, and then this other negative comment. So what is the polarity? What is the value of the intensity of the positive or negative reviews? And then the last one will be the no, this one. Sorry, I didn't change the name. So by right, this is the hand capture detection. So this is actually to use the skeletons library to identify the fingers. Okay, in the night mode as well as the day mode. So this is in the day mode. So later on, it will show the night mode. So yeah, you can even identify the fingers at the night mode. So meanwhile, the second student, she the same things, use the same libraries, but give some command to this skeleton. So right, for example, this is hello, this is okay, and so using a media pack library. So even identify the fingers, how many fingers are there? And then the last one will be the hand controller to control the website, the mouse cursor using the hand, using the finger. So you can see that turn on the YouTube, and you can see that the way he moved the hand, so they will see the cursor is also moving. Then he will bend the finger to click. expand again, so then you will good. Okay, so these are some of the works done by the students. It's actually not difficult. The libraries all are available in the Google, so you just need to pull out and then actually try your own data set for it and then do some testing using the library. Okay? It's not difficult. I think it's still okay. Are you?
Can you show me the first one back? I want to take a picture of the QR code. First one.
But this grammar, I'm not going to ask you to buy any stock using this predictor. I mean, just educational purpose. You study first. You can't even buy using this. Okay. So that's all for today's lessons. Any questions regarding to your maybe assignment or maybe to the chapter 3 on informed search? You try the question first. If you still don't know, you come back to me. How to expand the notes, right? What is open, what is closed, you still don't know, then you come back to me. Then we'll maybe you got time next week, then I will show you again. Alright. So if no more questions, then we will dismiss. We should have a happy holiday for Muslim. Any Muslim here? No more. You. Okay. Happy holiday. Okay. See you Thursday.
1个小时有吗？然后再见嘛。
How many of you cannot find in attendance?